is continuing on with our review with chapter 0. We're going to take a look at more fractals and what else fractals have to offer us. Remember, some of the famous fractals, or a couple of the famous fractals we've talked about. This is, if you can remember, pause for a second, think about what fractal is this. It's called the Mandelbrot set. So anytime you see this type of pattern, sort of circular pattern like this in fractal form, you're going to say that's the Mandelbrot set. Okay. A couple other examples of the Mandelbrot set. Again, they might look a little bit different, same type of pattern. Do you remember what this one is? This sort of a swirling pattern, like the eye of a hurricane. That is called what? Think about it. That is our Julia set. And remember, these things, these patterns are formed when you feed the equation back into the beginning. So you feed the answer to the equation back into the equation to begin with, over and over and over again. So something very simple, but you feed it back into that simple equation and you come up with this pattern. And this one is the Julia set. And again, you have that swirling pattern with the eye of a hurricane. So this again is the Julia set. And with the Mandelbrot set and the Julia set, just simply feeding the answer to one equation back into the beginning over and over and over again to get this pattern. All right, so hopefully you can tell from these, the two that we talked about, the Mandelbrot set and the Julia set, which of these does not belong. The Mandelbrot set being that more circular one, and the Julia set being the more swirling hurricane type pattern. So hopefully you can see we have swirling pattern, the Julia set. There's that circular set again, which means this one does not belong, neither one. All right, so remember our Sierpinski triangle. What is our recursion rule for our Sierpinski triangle? Again, recursion is just doing something over and over and over again, following the same rule over and over and over again. So what did we do with this triangle to form the Sierpinski triangle? What's the rule we follow? The rule we follow, if you recall, is simply connecting the midpoints of what? Connecting the midpoint of all the triangles, or connecting the midpoint of just the upward facing triangle. A very recursion rule. You can say that in different ways. This is the easiest way to remember it. So yeah, the midpoint connected those midpoints to form 3 new shaded triangles, right? 3 new upward facing triangles. If you go over here, we connected the midpoint of those facing triangles. Create all those upward facing triangles. So if we look at the Sierpinski triangle, this isn't something we've talked about yet. What's increasing in our Sierpinski triangle? What is decreasing in our Sierpinski triangle? Well, I'll give you a hint for maybe one answer you might come up with. What's the area? Depending what area. Which area, shaded or unshaded, is increasing? Which area, shaded or unshaded, is decreasing? Okay. We start out with shaded, and then we follow our rule to create these 3 facing triangles. The area of the shaded region is decreasing because we've taken a chunk out, if you can look at it that way, of that shaded region. So it looks like, as you can tell, more unshaded space and less shaded space. Right? So we have the area, what's decreasing. Start with this one. What's decreasing? area of the shaded region. Well, if the area of the shaded region is decreasing, that means the area of the shaded region is increasing. As we follow that recursion rule. All right, we're going to take this a little bit further now. So if we think about that Sierpinski triangle, if we look at stage 0, how many new triangles are there? One new triangle. We've created one triangle. I'm going to skip this and for the moment. We're going to get back to that. Let's look at stage 1. How many new triangles are there? Well, with repeated multiplication, this is just 3, right? Or you can say 3 times 1, but I'm just going to say 3. We haven't multiplied anything. Or we could say, I suppose we look back, we could say, well, we have 1 triangle, and then we have 3 triangles, so we could say 1 times 3. What is 1 times 3 in exponent form? So I'm going to move on to exponents. 1 times 3 in exponent form is just 3, right? So 3 to the first power. So recall from what you already know, that we have a base. So 3 is our base. That's what we're multiplying. And we have our exponents. And that's how many times we are multiplying that base. Okay? So we're going to multiply 3 1 time. So remember, base and exponent. So let's move on to stage 2. How many new triangles are there now? We're splitting the shaded triangles into 4 triangles, and there's 3 new upward facing. New triangles, right? Well, in repeated multiplication, you heard it a second ago, maybe 3 times 3, right? 3 triangles on the top, and 3 of those total, so 3 times 3. Well, what is 3 times 3 in the exponent formula? And if we do our exponent, 3 is our base. How many times are we multiplying that? 2 times. So 3 to the second power, or 3 squared. Well, let's look at this next one. Times 9 times 3. And really all we've done then is take the last step. So 3 times 3. We just put that one again. Now 3 times 3. In exponent form, we have 3 to the third power, or 3 power cubed. Okay, 3 cubed. Okay? Alright, so now we have to run up. So you can put parallels here. So that's 3. 3 times 3. So this one will be 3 times 3. We follow that pattern. What is 3 times 3 times 3 times 3? So let's do a little mental math. 20 times 3 times 3. 20 times 3. Don't know how many times 3 is. Okay. Right, in a form, 3 to the 4th power. So notice this is 3 to the 4th power, and this is stage 4. So if we're going to use a variable to represent what's happening here, we could say that, and it looks like I already have that written down, we can say that we just have 3 to the k power. If it's stage k, 3 to the k power. Stage 4, 3 to the 4th power, and so on. So that's your recursion rule, 3 to the k power. All right, so let's think about this now with the Sierpinski triangle with another pattern. So here we just have a square. Move this up a little bit. So consider the number of new white squares. So it looks like at stage 0, 1 new new white square, right? Or you know what, I forgot to do something in that last slide. I'll do it here. I won't forget this time. All right, so we have one new white square, right? Again, I forgot to do this before, but I'm going to leave this multiplication form and exponent form blank for a moment for stage 0, and then I'm going to go back. Multiplication form, that's just going to be 1 times 5. Right? In exponent form, 5 to the first power is just 5. Let's go to stage 2. So now I have 5 times 5. So that's going to be like we said, 5 times 5, or 5 squared. Right? Again, I'll get back to that first one here in a minute. So if we go to stage 3, let's just do stage 3. So it looks like this is times 5 times 5 times 5. So 25 times 5. 25 times 5 is 25. And again, repeated multiplication form. 5 times 5 times 5. And that's going to be 5 cubed. So 5 is my base, 3 is my exponent. Make sure you have those two things written down, base and exponent. Even if it's review, please write it down. So now here I'm going to go back to the top, just to remind you of something. So what about at stage 0? So I'm going to jump to exponent form for stage 0. Well, it looks like at stage 1, my exponent is 1, stage 2, my exponent is 2, and so on. So at stage 0, following that pattern, I would have to say that at stage 0, my exponent is 0, 5 to the 0 power, right? Okay, well, do you remember what anything raised to the 0 power is? Anything raised to the 0 power is 1. You can see I have 1 new square, 5 to the 0 power. Anything raised to the 0 power is 1. Please, please, please write that down. So how many new white squares would I expect to see for stage 100? Yeah, stage 100 is going to be 5 to the 100th power. We're not going to write that out longhand because that would take kind of a long time. 5 to the 100th power. How many for stage K? For stage K, again, if the exponent goes by stage, this is going to be 5 to the K power. No matter what stage that is, that's going to be K. All right, and we're going to stop there for today.